And so how can we carry the same type of method to a chaotic simulation? And here the problem comes. The problem is about the statistics. This is a very simple model of a chaotic system. If you look at how the statistics of the simulation changes as you change the design parameter, when you first see this, it looks completely random. Why does it look completely random? Because for a simulation, you can only perform for finite time. Your statistics is an infinite time average. So here I only perform t to 5. Of course, you don't get a very good statistics, and that can totally explain this noisy behavior. So let's run it for longer. Let's change this 5 to 50. And you can see you shrink the noise by a lot. And let's increase this 50 to 500. Now you further shrink the noise. Let's increase to 5,000. Okay, now you see I get a almost smooth shape with a local minimum. But this 5,000 is really too much. I mean, this is about 5,000, the longest time scale in the system. So in CFD calculation, think of if you do 5,000 flow-throughs in your calculation, that's very expensive. And what we want is really a method that can give you the slope of this long time average, but with a much shorter calculation. Something, okay, but what we get actually is the derivative of the noisy simulation. So when people in NASA applied the adjoint method to the long time average of just a two-dimensional chaotic simulation, a separated flow over an airport, we get derivatives like that. So this is the sensitivity of the lift to angle of attack computed with the conventional adjoint. As you increase in the number of time steps, you don't see here, this is 10 to the 15. You get huge sensitivities. That doesn't make sense at all. Like, what is the derivative of CL with respect to alpha you would expect as an aerospace engineer? Huh? 2 pi based on thin airfoil theory, but order 1, right? Here, it's not. It's 10 to the 15. And the same thing happens when this is actually the case, the same case that JJ has read. So in NASA Ames, we had this is the adjoint field of a low pressure compressor. And you can see the field just grows as time increases. Let me see if I can play this again. Anyway, so yeah, so this field simply grows, actually, if you look at the magnitude, exponentially in magnitude. And the derivative you get doesn't make any sense anymore. This problem is not just for CFD calculations. So this is a MATLAB program. This is my entire simulation, just a few lines of MATLAB code. It is one of the simplest chaotic dynamical systems you can simulate, the Lorentz system. So it has parameters S, R, and T. I'm simulating this for 100 time minutes, taking a time step of 0.01. Did people here study numerical methods? How many people study numerical methods? Okay, just a few. So I'll go over this very quickly. So these 3 lines are the dynamical system. We've got 3 ODEs, and I'm using forward order to integrate this. So this Z mean is exactly the long time average I wrote down as mathematical formula. It's the integral divided by dt. Okay. If I plot the trend, this is one of the parameters. I fix the other parameters and look at the Z mean. So this system describes the chaotic heat transfer between a hot plate below and a cold plate above. So there are vortex rolling up and things like that. So R is a non-dimensional temperature difference, and Z is the amount of heat transfer happening driven by the flow field. So taking the mean is like what is the long time heat transfer driven by a temperature difference, and you expect this to go up almost like linear, right? So what is the derivative of the Z mean to R? What do you think? Based on your eyeball. things are all non-dimensional here.
Looks like 1.
Looks like 1, right? So the same scale. Okay, so let's have the computer do it. This is not even the adjoint, but it produces the same result as adjoint. So can somebody identify what method I'm using to take the derivative here? I'm running this 2 times, one with the R0, one with R1. And the difference between R0 and R1 are different by 10 to the minus 60 J. That's imaginary number here. And I'm taking the derivative of that. What method am I using?
Looks like finite difference.
Looks like finite difference, but with a complex step, right? It's called the complex step difference method that allows you to take derivatives with very, very small step sizes and avoiding roundoff errors in numerics. So let's see what this produces. First of all, the sign is wrong. There is a minus sign here. And the magnitude is off by about 34 orders. All right. So what's the problem here? The problem here is something, really, if you plot this, you can zoom in and verify yourself. Is this line, when you zoomed out, looks like smooth. But when you go ahead and plot it with a very fine grid of R, you find out when you zoom in, it's very jagged. It's very jagged. And the further you zoom in, you find out the more jagged it is. The derivative of this line is probably actually this much. If you do the derivative at different R, you get almost like random numbers that are also random in the sum. So the real line is actually extremely jagged. And when you're taking the derivative, you are taking the real derivative of the noisy line, not the derivative of the long time average. But it's the long time average we want to differentiate, because if we want to do design optimization, this gives you nothing.